Thank you. Great. And I imagine everyone can see my screen. Yeah, okay, excellent. So I would like to start with acknowledging the traditional custodians of the land. We would like to pay our respects and acknowledge the Gadigal people of Eora Nation. That's where we are joining the meeting from. And we would also like to acknowledge all other traditional custodians of the lands from which you are joining the meeting from. And this is our agenda for today's meeting. We'll start with brief introductions, starting with the research team from Collaboration on Energy and Environmental Markets at University of New South Wales. The project team includes myself, David Saldivia Salazar, Hussein Saberi, Ruby Clisser, and Anna Bruce. All of them are on the meeting with us today. We have industry partners from Endeavour Energy, Solar Analytics, Ausgrid, New South Wales The Q, and Energy Smart Water. As well as we have Jenny and Scott from Race for 2030 Homes program, who has been supporting the project. And the project has been also participating in an International Energy Agency solar heating and cooling program, Task 69, smart water heating. And we have had a couple of presentations to a broader international audience as part of this project, as well as there was a session in Melbourne last year as part of Asia Pacific Solar Research Conference. Okay, so I will start with summarizing the main findings of the project, and then my colleagues will give you a more detailed explanation of each of these outputs and different aspects of the project. But before that, I would like to start with a little bit of a survey, if that's okay. So if you could go to this link, I could also share the link with you on the chat in case your mobile phone may not work. So let me just get that link up here. Okay. So we have a couple of questions, as you'll see. The first one being, what type of water heater do you have? The second one is about, are you thinking of upgrading your existing water heater system? The third one is about your specific electric water heating system. And the fourth one is a priority. And it would be great if you could rank them in order. So let me get the link up again, the survey link. For the ones who have joined the meeting recently, we are doing a little survey. The link should be on the chat, or you could also see the QR code on the screen. Okay, so I'll give one more minute and then we can check the results in more detail. Okay, I think we got decent number of answers. And if you haven't done so, please go and fill this survey out so we can get your answers in real time. So the first question is about what type of water heater do you have in your house? And we can see that most people have a gas instantaneous systems. And this also includes myself. We are renting at the moment. But so yeah, when we transition, I'll definitely walk the talk and potentially buy a heat pump. So this is not surprising because I've been having conversations with different water heating manufacturers, and they mentioned that their most popular product is the instantaneous gas water heaters. We will talk about these more during the workshop. The advantage of these systems is minimal heat losses compared to other systems with storage tanks. So the heating happens on the spot, but obviously there are higher emissions compared to some other technologies as well. Okay, and the second most popular is resistive resistive water heater with a storage tank and with PV timers or diverters. Great, thanks for your responses. The second question, are you thinking of upgrading or replacing your existing water heater? If your answer is yes, I would also like to get to understand what sort of technology you are thinking of. So majority isn't thinking of upgrading their systems, and maybe we can discuss this why towards the end. There are a couple of people saying yes, and also they have provided details here. Some of them thinking of um, heat pump or smart resistive electrode, PV hot water. So thinking smarts for their systems. Okay, thank you for that. The third question was, if you have an electric water heating system, I'm asking about this electricity connection. It's either on the general supply with the all remainder of the household loads and your PV is connected on that as well. It will either be on the control loads managed by the distribution network service provider or more recently the retailers. Some of you don't know, and most of you have gas, so it's not applicable. Okay. And wow, okay, so we have very close results for this one. So I've asked for you to rank in order. What is the highest priority that you expect from a water heater? And most of you want maximum reliability from your water heater with no risks of running out of hot water ever because you love your showers and baths, or your family does that. That's great. Thank you. This is closely followed by you want your bills to be a minimum, and you wouldn't mind if you run out of hot water every now and then. And this is almost equal actually now, 40% to 40%. Okay. And this one is about the emissions, and we care rather a little bit less about this one. So if I was to see this a bit more detailed, yeah. So actually now we get the second one, the water heating bills minimum, as the first choice, the highest one. So yeah. Anyways, can we have it all? Let's discuss. Let's get started with our project outputs. So we have organized this project to run in 4 parallel research streams: the thermal modeling, customer hot water roadmap, and network impact of hot water load on the network, as well as forecasting day-ahead hot water energy. The thermal modeling included working with Transys, which is an industry standard and highly reliable thermal software. This was integrated by Python, which allowed us to be more agile and be able to customize Transys in various different ways. We've also run different Monte Carlo simulations. So David on the call will be telling you more details about this. But in essence, we have modeled resistive systems with different PV solar soak options. We have modeled heat pumps, solar thermal, and gas systems, and compared their performance. We have also controlled different hot water load control strategies, including some of the existing control load strategies by networks, as well as some of our proposed solar soak focused control strategies. We focused on different water draw profiles. You can see different percentage of water draws throughout the day. Some of them are aligned with morning and evening. Some of them are more equally distributed throughout the day. We have modeled different number of people living in the same house, as well as climate of the household that you're living in, different capital cities. As a result, we're looking at annual water heating energy emissions, as well as the efficiency of the storage systems. So a couple of key results. According to our results, we have discovered that storage efficiency, which means the energy that you put in and the energy that useful water heating energy that you put out, and the ratio of actually the latter to the prior, around 67 to 72%. So this is thermal modeling results by Transys, and this has shown us there are significant energy losses from the tank due to ambient losses. Now, these are modeled with a standard tank, which David will mention the specifications. We believe that there are significant opportunities to improve here. And by simulating a more improved thermal insulation, we can achieve 15% savings in costs and emissions. We have seen that the heat pump average coefficient of performance ranges between 2.75 to 3.5. This is the base case for Sydney, also ranges differently in different capital cities. It is not only influenced by the ambient temperature, but it's also influenced by the water temperature in the tank. And we've found that heat pumps reduce emissions compared to a resistive system around 67%. If we add a solar soak component for the existing control loads, because there are more hours where the circuit is energized, we've seen that energy consumed by the water tank increases by 4.18%. And similarly, if we change from the existing old control load to an exclusive solar soak heating, the emissions reduced by around 17%. This is for Sydney. We've modeled different hot water draw profiles to cater to different consumer habits in the household. And some of them actually gives more predictable state of charge for the tank control. And we will explain this in more detail. We've also modeled hot water shortage risks based on different consumption profiles and climates, etc. And what we've seen that if we shift the entire water heating to solar soak periods, there are risks of running hot water. Therefore, we recommend to have early morning or late night heating to complement that. And that significantly reduces the risks of running out of hot water. Now, the second part of this project is a customer hot water roadmap. And as the name suggests, this is a tool that we are aiming to make it available to public and households, where basically people will be able to see their annual electricity bills, net present costs over a 10-year period, and payback periods if they wanted to switch from one technology to the other. And similarly, these variables apply here, the thermal modeling variables. And we're also considering the different tariff options, different state government rebates and incentives as well for different technologies. And as part of the customer hot water roadmap, these are a couple of plots here. And Ruby is going to present this in more detail, but we can get the annual water heating energy cost for different technologies with PV or without PV or gas under different control load strategies, or on general supply, or with the timer or diverter, etc. We can get the net present costs. We include initial capital costs, operational costs, connection, and daily supply charges, as well as the payback periods if we wanted to switch from one technology to the other. So these are the main outputs that households will be able to see. So we've done a significant amount of work in this space, but over the next 6 months, we will be developing this into an online customer-facing tool where people can go and enter their unique household circumstance and get bespoke suggestions and recommendations, so they will be empowered and informed about their hot water choices. Okay, the third aspect of this research is analyzing a real-world network trial, which is within Endeavour Energy Network in Albion Park region. This is called Off-Peak Plus. And basically, what is happening in this trial is we have around 9,300 households. The trial started with a less number of households, but now this has expanded. And some of these households are in default control load 2, which not only allows heating at nighttime, but also allows heating during the day, except the seasonal peak periods. So some retailers also have a really large proportion of these customers, and they have started implementing different control strategies within the trial. And Hussein will tell you all about this. On average, we've seen households use around 7 kilowatt hours of water heating energy. Around 28% of water heating energy was shifted to solar soak daytime periods, but this was mostly with default CL2. When the retailer in this trial started implementing their more refined technologies, we saw that on some of the days they could shift more than 70% of daily water heating energy to the solar soak periods. According to our financial analysis, we've estimated that there is around $27 per household of wholesale arbitrage benefits, which is instead of paying the entire heating at nighttime period, now you're paying some of it during the day with solar generation, which is much cheaper wholesale prices there. But these benefits are not being currently passed on to the households. Something related to this, we've discovered that the control load fleet has been reduced over the last years. Having discussions with different DNSPs, we've discovered that around 15 to 25% drop in our existing control load fleet. Some of the reasons, because households cannot self-consume their solar when their water heating system is on the control load, because they are physically separate electrical circuits, control load and where the solar is connected. So households would like to actually be able to do that. So they ask their installer to switch their hot water system to general supply. Also, some households may have transitioned to gas systems. So those are some of the reasons. At the moment, there is this new control load where retailers and networks are trying to incentivize more and more hot water load being shifted to daytime to soak up excess solar generation, which causes certain challenges like minimum demand, over voltages, curtailment. But for now, we haven't seen these advantages of cheaper daytime tariffs being reflected onto customers. So we are suggesting and recommending that if possible, retailers should propose new tariff designs, and the daytime component should be much, much cheaper. We have seen a couple of examples, only very limited, but it doesn't seem to be very reflective of what the potential is from that arbitrage. And also, we have so much utility scale curtailment in the network. Most of them are due to economic curtailment because the prices are negative in like South Australia, for example, or very low. So basically, we are wasting clean and affordable energy. We know some curtailment is inevitable, but we have these storage tank systems that could actually work really well with that. Okay, another part of this research was to understand the voltage impact of the hot water heating systems, and we've basically modeled as well as analyzed real world data. How do the hot water heating systems, when they're shifted into the middle of the day, are they effective in lowering network voltages? Can they be used as a voltage regulation service? So Hussein will talk more about this later on. And final piece of our project was forecasting day ahead hot water energy. And we have done this at the aggregate level, focusing on the entire fleet, as well as we have done this at the substation level, smaller number of households aggregation. We've worked with deep learning models, LSTM and CNN. And basically before building these models, what we've discovered, which is probably known by most of you, the hot water energy consumption is highly correlated with ambient temperature, which is one of the most important predictive variables inputs to be used in this forecasting problem. In addition to the ambient temperature, we use historical hot water consumption as well as the type of day when forecasting the day ahead demand of electric hot water. What our forecast models have shown that there is high accuracy. This is a coefficient of determination, and 1 being the maximum, 0 being the minimum here. And we have obtained quite promising values both at the entire fleet as well as at the substation level. Now, these are the key project findings that I've summarized. Now we will go and find out a little bit more detail for each of the stream. As I said, we will leave the questions until the end for the discussion sessions. Thank you. So David, if you can unmute and I'll help you with the slides.
Thank you, Baran. Yes, so I will talking about the thermal modeling and what we did and the main results we got from that. So next slide, please. So what are the thermal models that we are running and why we are using it? Well, we are simulating the domestic electric water heaters, but the most important part is the hot water tank. We have like a schematic here on the right. This is a typical hot water tank with the hot water outlet on the top, the hot water inlet at the bottom, and the heater and thermostat are also at the bottom. And at the beginning, it seems really simple, but there are several phenomena that happens here during the operation. We have a stratification that is desired, but we have several phenomena like conduction inside the tank, thermal losses, and natural convection that leads to buoyancy effect, etc., that affect this stratification and affect the possible the thermal capacity and the state of charge of the tank. So that's why we want to simulate this under real world conditions. And this is also important because this is the integration or where the conversion happens between the electrical side and the thermal side. That is the service that we are offering, the hot water service. We will do analysis in the long term, annual simulations for technical and financial variables. I will talk a little bit about the technical ones, and later Ruby will explain how we integrate this into the financial analysis. And we also look at the short-term analysis through Monte Carlo simulations for to study the hot water shortage risk. What are the main issues with the thermal simulations? In this case, is we have almost no real-world data for thermal variables. We have electrical variables, but temperatures and mass flow rates are not recorded that much, except by research and trials. And even if we have that, we have inherent uncertainties on the behavior and energy flows. So we cannot have full certainty about the results, but but we can provide like long-term results or a probabilistic approach. That is what we will show here. And of course, the other challenge is we have too many variables and too many options involved. So we want a flexible tool that allows us to change these parameters and obtain the results. Next one, please. So this is the implementation. We developed an open source repository that is, as Baran said, is based on Python and Transys. We are using Python for almost everything except by the hot water tank simulation itself, that we are using the Transys engine for that. The open source repository is available in the link that is shown here. There is our collaboration group research GitHub page is there. And for simulations, when we say a simulation, we are talking about 4 steps. We have the settings when we define the household location, the occupancy, the behavior, the system they have, if they have PV or not. Later we generate, we have a time series generation step where we generate the time series that we will use for the simulations. We run the simulations and get the output, and depending on what type of output we are looking for, we can have different post-processing. I will focus a little bit more on the generators, how we get the data from, and the models in the next slides. Next one, please. So I want to show like what we have implemented. In terms of time series generator, we have included the hot water dropper files. We are using 6 different hot water dropper files based on previous research that these profiles were compiled in previous research. We have the typical household profiles. For example, the typical one that we have hot water in the morning and on the evening only. That is the first one. If we have some consumption during the day, the second one. Evenly distributed through the day, focus on the morning, on the evening, and on the late night. And we also included the variability, the daily variability. This is like an intraday variability, and we have also the interday variability through the different days. We have different control strategies. As Varan said, we included 3 existing control loads defined by Ausgrid. The control load 1, that is nighttime. The control load 2, that is pretty much every time except by the evening peak. And we called control load 3, that is actually the new Ausgrid solar soak, that is the control load 1 plus a solar window. And in addition to that, we included 2 cases of interest, the general supply one, that the system is always connected, and the solar soak, that is what we propose for only solar soak time. We have the weather files. We are using with our norms TMY files for different cities. And for the market data, we are using energy plans from main retailers. And we are also importing data from other open source repositories developed by our collaboration team, that is Nemesis for wholesale market data and NEMET for the grid emissions. Next one. We also implemented 5 different technologies, as Varan already mentioned, resistive heaters and heat pumps. These are the most one that we're interested in, resistive heater being the traditional one and heat pump the disruptive technology. But we also modeled a gas heater instantaneous, gas heater with storage, and solar thermal collectors. And we included an optional PV system that is a generic 5 kilowatts system that is modeled by PV Live. Next one. And going to the results, we are considering a base case for a typical household in Australia in Sydney for 4 people. The other specification for the tank and heaters are there. And for the different technologies, we have the specifications for the resistive and the heat pumps. And the variables of interest in this case are the storage efficiency, the state of charge and each moment, the annual emissions, and the hot water shortage risk. These are the technical parameters. All of the financial and cost will be covered later by Ruby. Next one, please. So here we have results for the resistive heaters. On the left plot, we have the storage efficiency. On the right plot, we have the annual energy consumption. The x-axis are the different control strategies, and the different colors represent the different hot water dropper files. So we have a storage efficiency between 65 to 70%, and the annual energy consumed is around 3,000 kilowatt per year. The whole bar is the energy, the total energy provided by the heater, and the red bar, the red line, is the energy consumed by the household as hot water. And the percentages that are there are the what is the energy increase if we move from control load 1 to the other alternatives. And we can see here that the control strategy has higher influence than the hot water dropper file over the storage efficiency, as we can see on the left. These are annual results, but we can have also detailed results. For example, on the bottom left, we have the first 3 days of simulations with the different temperatures. And with that temperature, we calculate what is the state of charge. I will talk a little bit about the state of charge at the end of my presentation. Let's move to the next slide, please. We have the results for the heat pumps. We have similar results in terms of annual energy consumed and storage efficiency. Similar results in terms of annual energy delivered by the heat pump compared with the resistive, but the energy consumed is actually way lower because, as we know, the heat pumps consume less energy than the heat that they provide. In this case, the whole bar is the total energy delivered to the tank, and the shaded one is what is the electricity consumed by the heat pump. And the ratio between both is the coefficient of performance, that is the plot that is on the right. So again, we see it seems to have a higher influence, the control strategy, than the hot water dropper file. And the solar soak and control load one, that is the nighttime, are the best performing one. And the reason for that is because they have a uh, eh, lower number of hours on the heating period. And that means the temperature on the tank is relatively lower, reducing the heat losses. And because this temperature is lower, the heat pumps operates closer to the design point. Uh, it's what is important here is the design point for the heat pump we are simulating. It's a Reclaim Energy heat pump is 6, but the results show an average of 3, around 3, and that is because we are operating far away from the design point. We wanted to check also what's happening in different cities. So on the plot on the right, we have different colors. In this case, the color represents the cities, and we see that the different cities have same trends. And again, the control strategy seems to have higher influence than the city, and the city's influence is given by the ambient temperature. So it seems that the control strategy has a higher influence than the ambient temperature in this case. Next one is regarding the emissions. As I said, we imported emissions from the grid from NEMED for the different Australian named regions. So here we are presenting the result for the resistive heaters and the heat pumps. Again, the colors represent the different cities. So the main results here is if we want to reduce emissions, the best option is moving from resistive to heat pumps, 67% of reduction on average. If we cannot do that, the name region is really important. So Adelaide, for example, have 20% of the average emission than Melbourne, and that is because of the grid's composition. But the third option is moving to the middle of the day and switching from the CL1 on to solar soak. In this case, at least for Sydney, represents a 70% of reduction. Similar reduction are found in the other states as well. And next one, please. And regarding the Monte Carlo simulations, so far what I have presented is the long-term analysis, like in the long term, which alternative is better. But in the short term, if we are on the household point of view, the interest is, for example, not running, avoid to run out of hot water. So if we want to estimate that the hot water shortage risk, we need to analyze what happened on the next day, for example. So for that, we used Monte Carlo simulations. I will just explain briefly what it means, but the basic idea is a stochastic approach. We have several variables that the one presented on the left that we don't know. We don't know exactly what the variable will be, but we have certain probability distribution. So we generate a certain amount of typical days, possible days for each case, and we simulate them and check what is the distribution of the outputs. So in this case, for example, this is one case that we are hitting in the middle of the night. So we have the state of charge on the plot on the center. We have the state of charge that is up to 1 on the middle of the night, and later we see what's happened during the day. And each day, because we have different consumptions, we have different results, and we collect the result at the end, and we have the distribution of the state of charge. And what we are interested in is what is the probability of the state of charge being lower than a certain threshold. In this case, we're using 10%. So the probability of having a state of charge lower than 10% is the hot water shortage risk. But we don't want to know this only for a timer on the nighttime. We want for timers with different duration and that start at different time during the day. So the next one, that is my last slide. So we simulated here a lot of different cases with different timers. So for a household, for example, we can see a different timers duration, 3 hours, 5 hours, 7 hours, and 9 hours on the different plots, on the different heat maps. For the 6 different hot water profiles, and what happens when the timer starts at a certain point, and we quantify the hot water shortage risk. So we see that above, for example, 7 hours, there are almost no improvement on the hot water shortage risk. And we see that for most of the hot water profile, during the daytime timers works fine, except by the hot water profile 1 that we have a higher shortage risk on timers starting during the day. So this is the case, for example, that Varan mentioned that we might want to add a nighttime window for additional heating. So, yep, the next one, please. And these are the main takeaway points. It's briefly what I have mentioned in my previous slide. So if you want to discuss something, we can go back to this one. But yeah, this are the main takeaway from this part.
Thank you, David. Ruby.
Yes. So are we talking about the customer hot water roadmap? Next slide, please. So the goal of this roadmap is to assist customers with understanding all of the different water heating and control strategy and tariff options available to them. The roadmap will consider a lot of different variables, including different water heating systems, households with and without PV, different tariff options, control strategies, usage patterns, any associated costs, savings and rebates depending on a household's location and size. So the way that, next slide, please. The way that we've gone about the approach to this roadmap is using David's thermal modeling to get the performance data and the operating costs for the different water heating technologies paired with research data. So we get the water heater specifications from the different manufacturers, and then the supply and installation costs from different retailers. We get the tariff data as an average from AGL, Origin, and Energy Australia rates, and any rebates from the government for state-specific rebates as well as national rebates, to output the financial analysis where we get the annual water heating bill, the net present costs, and the payback period for the different technologies. Next slide, please. So in this roadmap, we consider lots of different variables that will affect the household. So we look at the different locations, the hot water draw profiles, as David explained earlier, the household size, PV ownership, all the different water heaters that David mentioned previously, as well as a cheaper heat pump option. That's the iStore heat pump, the different control strategies and the different tariff options. And then there's a more detailed breakdown of the different control strategies that David explained earlier as well. Next slide, please. So for this analysis, we have a lot of different assumptions, and there's more details available in the appendix if there's more assumptions that you want to look into later. But the main ones are that the control strategy is modeled with self-consumption, which, as Baran mentioned earlier, isn't currently possible as they're set up on different circuits, but it shows a possible case in the future where switching between these circuits are possible. We also look at the solar feed-in tariff, which we consider as the missed opportunity costs when solar energy is used by a household or used by a water heating system rather than exported back to the grid at the solar feed-in tariff rate specified by energy retailers. And then for the daily supply charge, we don't include the daily supply charge for all electric systems because we assume households will be linked up to electricity regardless of their water heating system. And then specifically for controlled load tariffs, the DNSPs have an additional daily supply charge for controlled load systems. However, that's not passed on by the energy retailers, so we haven't included that in the pricing for this analysis. And with gas, we do include the daily supply charge because maybe it is just for water heating, and we've assumed that if a household were to switch to an electric water heating system, they'd still incur that gas daily supply charge and they wouldn't close their gas account. And so those are the main assumptions. Next one, please. These are the cost assumptions. So for all of the technology, supply and installation costs, we researched that from different retailers. And then from industry discussions, we've put together what we think the maintenance costs would be for all the different water heaters. So we've said that's around every 4 years, and for all the systems with a tank, that would include a full anode replacement as well as general maintenance. So yeah, next slide, please. Then we look at the tariff and rate. So this is for specifically Sydney, so Osgrid DNSP. And as I mentioned earlier, it's taken as an average of AGL, Origin and Energy Australia prices. And the gas tariffs are taken as the Energy Australia prices. And that's, yeah, all of the tariffs that we use for this analysis. And now we'll look at some of the results for this roadmap. So it's a bit of an overwhelming plot, so I'll break down what everything's saying. So the darker color for each shade is the system with no PV, and the lighter color is the system with PV. So the blue ones are the resistive heaters, and the brighter green is the premium, more expensive heat pump. That's the Reclaim Energy heat pump. The next, more drab green color is the cheaper heat pump option, which is the iStore heat pump. The purple is a solar thermal system with an electric boosted heater. And then we have the darker red and lighter red are gas instantaneous and gas storage systems. So on the plot, the bit with nothing on it is the usage costs. Then we see on the gas systems that daily supply charge that I mentioned, that's the ones with the spots on it. Then we have the vertical and horizontal cross is the solar feed-in tariff that I mentioned earlier. That's the missed opportunity costs from the solar feed-in tariff. And then on the cases with PV, we see the solar fraction that shows the energy contribution from solar for the different technologies. So the standouts from this plot, we can see that the heat pump with a timer solar soak is significantly lower than any of the other usage costs. It's quite a low annual bill for water heating. And we can also see the difference in all the cases between the premium heat pump and that cheaper heat pump. And we can see that, the usage cost for the premium heat pump is quite a bit lower than the cheaper heat pump, that ice or heat pump. Additionally, if we look at the gas instantaneous column, we can see before the daily supply charge, so just the usage costs, it's quite low and it does compete with the more efficient electrical water heating options, which was a bit of a surprise to us when we were doing this research to see that it does actually compete with the electrical models. And then that brought about the discussion of introducing emissions data into this analysis as well, which we haven't yet included, but I'll discuss later on. So the next slide looks at the net present costs over a 10-year period. And again, I'll explain everything, but it's interesting to compare the annual bill to the 10-year period and see how the different things change over that long period and including of all the different costs. So again, the darker color is no PV, the lighter color PV, and we have the resistive heaters in blue, the heat pumps and all of the other technologies that are listed here. Then with the markings on the plots, the circles are the initial costs, so that includes the supply and installation costs and any rebates that may be available for each water heater. In this plot, we're just plotting a household buying a completely new system, not upgrading from a previous system. So there's no rebates included for any upgrades or anything like that, but there are rebates like the small scale technology certificate rebate. That one is included in this because it's eligible on new systems as well. Then the next plot is again just the usage cost with no marking on it. And then the diagonal cross is the maintenance cost based on the cost assumptions table that I showed earlier. And then we have again the daily supply charge for gas systems, and then the solar feed-in tariff from the missed opportunity costs for the systems with PV. And so the standout, one thing that I should mention as well is the warranty for the premium heat pump is 10 years. So this is modeled over a 10-year period. However, for the cheaper heat pump, it's only 4 or 5 years, and a reinvestment in a cheaper heat pump isn't included in this. So it's just the initial costs for one of the cheaper heat pump options. I think what is interesting to see is that for resistive heaters, the main cost over the 10-year period is the usage cost of the system, whereas for heat pumps, it's definitely the initial costs and that high investment at the start that is again not inclusive of any rebates. And yeah, those are the net present costs. And so to help customers understand it and use this information from the tool, we've included the payback period, which is the next plot. And so this is upgrading from a resistive heater. And we've said it's at the end of life of the resistive heater. And we've assumed that a household with an electric system would only be upgrading to an electric system as well. So we've showed the options for the premium heat pump, the cheaper heat pump, and solar thermal options. And because it is upgrading from a resistive heater, there are the ESS rebates included in this analysis. So yeah, we can see that all of the payback period does fall within the warranty or the lifespan of each water heating option. And yeah, we'll hopefully just help advise customers what their best option is available to them. And so yeah, the next slide, please. So for in the future, this tool will be developed into a customer, like a tool that an online tool where customers can use it and input their data and their conditions and gain insight into their specific situation, and all of their options are available to them. So to use a large lookup table and they can match their cases. And as I mentioned earlier, we'd like to include emissions results in this so they can compare water heaters, not just on the financial side, but also on the emissions result. Currently, we're just looking at the major cities. So we've got results for Melbourne, Brisbane, Sydney, Adelaide, and Canberra, but we're going to include other major cities as well as different rural locations based on climate. And yeah, that's the customer hot water roadmap. Thank you.
Thank you, Ruby. Hussein.
Thank you, Baran. So I present the real-world data analysis and from Endeavour Energy for their off-peak plus trial in Albion Park and also other zone substations across New South Wales. So basically, we have two types of data: the market data, that is the energy consumption on a 5-minute resolution, and the PQ data, that are the voltage measurements of either instantaneous, average, minimum, or maximum on a 5-minute time period. And this plot shows the number of customers with available market data or PQ data at each timestamp over the year. As we can see, for most of the year, there is consistent number of customers, around 7,300 of the market data, but it's not so consistent, a little patchy for the power quality data. And the other fact is that for most of the customers, these data are not available unless late September 2023. Next slide. Yes. In the next slide, we see the static control strategy of Endeavour Energy for 2 days as a sample. Basically, it depends on the month of the year and day of the week. On the top graph, as is Friday, a weekday. So there is a nighttime window, starts from 10 p.m. and ends with 7 a.m. in the morning. And there is a solar window that starts from 9 a.m. until 5 p.m. But on the weekend, it's almost on at all times, except the peak evening from 5 p.m. until 10 p.m. Yeah, in the next slide, we see the dynamic control strategy of a specific retailer that represents 37% of these customers from 8th of September. So in this plot, the energy price is shown by the yellow color. Here we see that despite the fact that energy price is quite volatile during the daytime, but the retailer, the green one here, has been able to smartly shift their load to the periods with lower energy price. There are some instances, like on the bottom graph, that this is not true, so they couldn't actually match this. But overall, from the whole analysis, we can see that they have been successfully predicting the energy price and managing to shift their load to values of energy price. In the next slide, we see the daily percentage of shifted hot water load to the daytime for these two groups, the retailer and the rest of Endeavour Energy fleet. And it's the same for both of them until September. And from that time, we see that how the retailer is performing. It's significantly shifting higher amount of load to the daytime, especially in December, that can go over 70%. And this strategy over the whole year as an average leads to around 1 megatons of CO2, that is equivalent to 8% emission reduction in New South Wales. In the next slide, we see a financial analysis that is basically we are estimating the revenue from price arbitrage per customer for these two strategies, the default Endeavour Energy and the dynamic control of the retailer. And by price arbitrage, basically, we mean the difference between the cost of energy under the current scenario, that is some portion of the load is shifted to the daytime, and the hypothetical scenario that all heating is being done during the nighttime. That is the traditional CL1 scenario. As we can see during the different months, this benefit can change. It depends on the amount of load being shifted to daytime, and also the difference between the energy price of the daytime and nighttime. But the point we can observe is that from September, and especially in October onwards, the retailer has been doing more significantly gaining benefit from this price arbitrage. Especially in December, that the difference is like more than twice of compared to the default CL3 of the Endeavor Energy. In the next slide, we try to understand the impact of hot water load operation on the distribution network. The top graph shows the hot water load of a sample household on a sample day. The blue one is the hot water load, and the red graph is the voltage profile. So it is obvious that the hot water load operation is accompanied with a drop in the voltage profile. And the amount of this voltage drop depends on the amount of water being drawn, that is the rating of the hot water system, and more importantly, the voltage to power sensitivity of the network. That is an indication of the network strength. So the stronger the network, the less voltage drop we observe. And when we do these calculations, we calculate the voltage drop for each on-off operation of the hot water tanks for all customers in the year. We come up with the bottom distribution. And what we can observe from this distribution is that actually the voltage drop is quite small. The median value here is just 1 volt, and 95 percentile is 1.4. So it shows that the network is quite strong, and I think it shows that it can integrate more renewables. In the next slide, we try to understand the feasibility of using hot water load as a voltage regulation service. And to determine this, we have to calculate the correlation of voltage profile of customers on a particular part of the network, such as those connected to the same LV transformer. As an example, this plot shows a highly correlated LV network. On the top, we see the hot water load of 6 customers on the same LV transformer. And on the bottom graph, we see the voltage profiles. As we can see, these voltage profiles are highly correlated. That means if operation of one household, the hot water system of one household, brings down the voltage of that household, it can also impact the rest of the households on that LV network as well. So this is an example that actually the hot water load operation can be used as a voltage regulation service. But to do this and understand this for the whole network, we do these calculations for several LV transformers. In the next slide, we draw these calculations as a distribution over 14 LV transformers. As we can see on some of these, like T1, this correlation is quite high. The distribution for all of the customers is quite high. But on some of them, like T2 and T5, the correlation index can vary significantly. On some of them is poor, on some of them is too high. So these are not ideal for using this hot water load as voltage regulation. But we can see that the network is quite strong on the rest of them, and those are the extent that we can use hot water load as a voltage regulation service. In the next slide, we did some network modeling for the Albion Park network using Dixieland Power Factory. Basically, we are simulating four load shifting scenarios. The CL1, that is all load being done during the nighttime. CL3, 25, that is 25% is shifted to daytime, 50 and 75. And on the bottom graph, we can then observe the 99th and 95th percentile of the voltage profile at each timestamp. In the next slide, we try to do these 4 simulations for 4 scenarios of shifting load to daytime, but under 4 case studies. So there is a lot of content in this graph, but basically we are going to understand 4 case studies. In the first one is that these 31 households on a LV network that has 109 customers are all resistive. That is the base case. So then we can observe how much voltage is being dropped by shifting load to daytime under these 3 scenarios. In the next one, the case B, we assume that all of these 31 became a heat pump. And the result is that the amount of voltage drop significantly drops as heat pumps consume a smaller energy. In the case C, we assume an extreme case of electrification that all of the loads, 109 customers on this LV network, became resistive with resistive heater. And as a result, we can see that there is a significant amount of voltage drop. We can compare it 3.8 to 1.6. Right? So there is a difference, significant difference. But the fact here is that even all this electrification, if we use just a simple randomization that is being currently done, we end up with a peak that lasts only for a couple of hours and not the whole solar peak window. So it shows that still the use of smart meters and more intelligent control strategies is required. And in case D, we observe that if all of these become a heat pump, then yeah, there is still, we see the reduction in voltage drop. And this amount is comparable with case A, that these are 31, but all are resistive. In the next slide, we study load forecasting of hot water load for the next day at the aggregate level. This graph shows the daily total hot water demand, and the blue one here is the mean temperature at that day. So basically, there is a pattern here that lower temperature have a higher hot water load, and vice versa. But there is also another pattern that is the day of week, that is a control strategy. And these spikes on the hot water load are the weekends that the amount of load is significantly higher. So it seems complicated, but from experiments, we see that deep learning methods can with high accuracy, predict this next day hot water load. On the left, we are looking at the scatter plot that on the horizontal axis is the actual ground truth, and on the vertical is the predicted values. So we see that our predictions are very close to the diagonal line of perfection. And this is equivalent to a R2 score of 0.956 and a mean average percentage error of 4.1%. And on the bottom graph, we also show the energy, actual megawatt hour at each day. We are using 2 weeks for training and 2 weeks for testing. So half of the data for training, half of the data for testing. And it is quite significant that the model can with high accuracy predict, especially those spikes of the weekends. And I think that's all, Warren.
Thank you, Hussein. Now we will wrap up our presentation so we can move on to the discussion section. Just a couple of key points. So you have seen these 4 pillars of our research. The bottom line is we would like to continue doing more research in this space, and we are keen to pursue with an extension for this project, and we're looking for different collaboration opportunities and partnership opportunities. A couple of to-do list on our in the very soon. So the next 6 months, we will be developing this customer hot water roadmap into an online public-facing tool. And we will need further funding beyond this 6 months to continue to maintain this tool, improve, so that broader public, government, industry, and academia all can use and benefit from this. And this is quite an important point for our strategies for future electrification. And as some of you may know, heat pumps are gaining more popularity. There are more options now in the market. So we would really like for households to make the most informed decisions for their unique cases. So that's an important objective for us. We have started discussions with hot water manufacturers. So there is an interest on what's next in this flexible hot water space. What do we need to do? We've identified that there is an opportunity with improving the insulation of the tanks or pipes may significantly improve the energy efficiency. So we may actually gain quite a lot. Perhaps this is the next low-hanging fruit, but there will be some additional costs with better insulation materials. And we would essentially, after having more information around this, like to do some submissions, have some submissions to the relevant standard bodies in Australia. As Hussein mentioned, the control of these hot water tanks can be improved, both for more smoother and effective voltage profiles, as well as heat pumps also requires different, more refined controls as well that we would like to continue working. We have the intention to utilize our hot water forecasting models for the broader industry use. We've already received some interest from AEMO and other DNSPs. How can these models can actually help in planning or for their day-ahead operations, or integrating and controlling consumer energy resources. There's more work to be done on the investigating the network impact and potential voltage regulation services of hot water systems. We would like to continue our modeling and real-world data analysis, considering different future scenarios of different rooftop PV ownership, different heat pump ownership scenarios, resistive ownership scenarios. So yeah, the bottom line, if you think this is aligned with your objectives as an industry partner or government, please get in touch, and we would like to continue discussions for future collaboration. Now, it's time for us to wrap up, and yeah, pass it on to you if you have any questions. And Scott Barnes from Race for 2030 will facilitate this section. So over to you, Scott.
Thank you, Brian. Thank you, Brian, and thank you to the rest of the team for a really great presentation. Certainly, there's a lot of material there, and so for those that aren't aware, this report will be published in a few weeks' time with the final report of this research on the Race for 2030 website, and I dare say also on yours as well, Brian. Going to the questions that we've got so far, and if others have any questions, please put them in the chat there, starting with a question from David. He is asking, are you able to model the hot water supply risk under extreme events using historical data? Has that been looked at? Question to you, David.
Yeah, so it's able to incorporate historical data on the models. What we have run some cases with using MERA2 reanalysis datasets but yeah, if we have historical data to see for extreme events, it's possible to incorporate it. The weather model have 4 different options. One is the annual simulations that I have shown, the Monte Carlo simulations, historical, and one to run some parametric analysis with constant variables. So yeah, it could be possible, and it would be interesting to look at that.
Thank you, David. A question also to you, David, from Robert, is whether a minimum duty cycle was defined when modeling the heat pump hot water efficiency, the coefficient of performance.
Yes, so we didn't include a minimum duty cycle for these simulations. That's the short answer. But what we have seen is that because usually heat pumps operates a little bit longer, so when the heat, at least on the simulation results, when the heat pump turn on, it usually operates for a little bit. So we didn't have to set a minimum duty time.
Maybe to clarify, David, when you say a little bit, we're talking hours or minutes?
No, we're talking about hours. Like that is usually the period,
Yes.
starting period of
Yeah.
half an hour.
Yeah. Okay. Thank you. A question from Brad, just a shared comment that Western Australia does not offer a controlled load option for hot water. And a question here from Brad also. Oops, it just moved on me. But when you talk about using water heating load shift as a voltage service, do you mean a separate paid network support service or as coincident benefit that accrues anyway with solar circuit behavior? Maybe a question for you,
No,
Baran. Sorry, go on.
yeah, we mean a separate network support service to generate value for a retailer, because that from a study we can see that this control load is highly predictable, unlike other types of load like HVAC system or etc. These hot water loads are highly predictable and they are controllable. And so we thought that DNSP might be interested in it. But currently, these voltage regulation services are not being traded on the market. So we did it as a research to show the feasibility to inform the DNSP for that.
Thank you, Hussein.
I have another quick point. Thanks, Hussein. And Brad, thank you for the question. And yeah, our apologies. We haven't got to the Western Australian part. It's mainly because the partners we work with, they're all this eastern coast of the Australia. But yeah, we would be also interested to look at Western Australia and include capital city Perth there. So yeah, would be interested to find out what the DNSPs in Western Australia. I guess it's Horizon and there's one more that I can't remember. My apologies. But what is their attitude towards the electric water heating systems? There is no control load, so that means all of them are on general supplies, I imagine. Or if not, yeah, we should perhaps have a chat, or maybe you can answer that as well. But we would certainly be interested in looking to Western Australian case as well.
Thanks, Brian, and thank you for the question, Brad. Obviously, more that can be done there. Question from Paddy. What is the current status regarding a common standard for interfacing with available heat pumps to dispatch control? For example, what are the options for sending control commands to the heat pump? Also, does this interface inform of the tank temperature for informing the amount of time until critical hot water level would be reached?
So I'll attempt to answer this question, and if anyone else have further comments, please feel free. This really depends on the manufacturer and technology of the heat pump. So there are some heat pump models out there that are highly capable in terms of operation and responding to different signals. I believe there are two different ways to control these heat pumps. The inherent native software that the heat pumps come with, and users can even choose from different heat pump menus if it is available to set a timer, for example, or different sets of timers at daytime and nighttime. So that's one of the control available. The other control that we have looked into this trial and in another project as well is basically smart meter control. So in that type of control, the interface is not necessarily communicating with the heat pump itself. It's just a cloud communication controlling the smart meter, and smart meter has a separate circuit. It's to kind of turn the heat pump on and off. So it's a more crude control. In terms of sending control commands to the heat pump, as I mentioned, it would depend on the manufacturer. I don't want to name specifics, but some manufacturers have this capability, and some of their models may not. So it depends on what are we expecting. And again, tank temperature information is measured on some more advanced units, but for most of them, especially these, as Ruby mentioned, there are cheaper heat pumps being offered. I don't think this sort of information or interface is available for these brands. But if there's anyone else would like to add, especially from original equipment manufacturers in this call, that would be most appreciated.
Thanks, Brian. A question here around potential future work. It might be outside the scope of this work, but has the voltage impact of solar hot water shifting and EV charging with solar being considered? So I guess I'd probably answer that and say at this point in this project, no consideration of EV charging. Certainly within RACE, we are interested in the co-optimization of different loads within households and the interoperability of that control, where currently a lot of the controls are independent to each of the devices rather than being collective. And so if you have some interest in that, Brad, or others on the call, certainly would be interested to hear from RACE. RACE would be interested to hear from you on that as to potential research that we could pick up. From Paddy, what is the current status regarding a common standard for interfacing? Oops, we've just done that one. Gareth, questions on hot water heater use. I think it was higher in the winter. I have heard of different opposite trends in different data sets in New Zealand. Have you done any disaggregation of how much is energy service demand, i.e. how much hot water people use, and how much is delta T on hot water temperature versus inlet temperature and storage temperature versus ambient temperature?
David, did you want to answer this question? I can bring the plot. I believe showing the heat losses that you have identified might be helpful in that total energy, and maybe we can further delve into it.
But I think this question is about the forecast, the hot water forecast.
Not forecast, but actual. But I think if I'm reading it correctly, there that more hot water is used in winter, or more energy is used in winter than in summer. How much of that is actual hot water being used versus more energy being required to heat water coming in at a colder temperature and a higher delta T heat loss to the atmosphere because of the ambient temperature being lower?
So, David, yeah, it's not about forecasting. I will just bring this plot up, and I don't think in this plot we show any intra-seasonal variation, if I remember correctly, but maybe you could further break down if you have any further plots we can show. So, Gareth, basically, as David presented here, and David, please correct me if I'm wrong on this one. This red line is the useful energy as a hot water service, and this is the total energy that is consumed by the water tank. And so the proportion above this bar is actually the heat loss, right? And there are different heat losses on different control load strategies. Now, and we've also shown this for the heat pump technologies as well, due to COP. It's much less what they consume versus what they deliver here. In terms of your seasonal comment, so
there was a graph around further through. It was a line graph with
this one.
Keep going.
It was on same part.
But I don't think it was
keep going. Yeah.
Yeah, okay. Not this one. This is the bills, the revenue.
No, keep going.
Okay.
Yes.
That one.
Okay. Yeah, so exactly, hot water demand is higher during winter due to lower temperature. And so you're asking what percentage is actual higher water usage versus what percentage is to bring that lower mains temperature to the ideal temperature. I understand your question.
And the loss of heat, standing loss as well, because you're looking at the power consumed, not at the hot water use, but you're inferring a water use from the power.
No, I understand. So from the real world data, it's difficult to infer that, but from our thermal modeling software in Transys, we can easily do that. So that's our answer. And but I don't know, David, would you have any opinion on, like, from your simulations? So if you have time series simulations, maybe we could look into this in more detail and let them know later on. We have the mains temperature, we have the ideal water temperature, we have the usage pattern. So if you know the answer, I'll please further elaborate.
So we didn't present like disaggregated data for seasons, except by the hot water shortage risk I showed that I think I didn't mention during the presentation, but it's that is for a critical case on July, like a typical day on July. So that is for winter season. So in that case, we focus mostly on that critical region, critical period of time. But we didn't present here like the disaggregated between for each season. But it's something, as far as something it's possible to do. It's just we need just to disaggregate and see what is happening.
Yeah, it is in our capability. And from like reading literature, and I would be very keen to understand what the other trends are in New Zealand or in other data sets. Generally, people tend to have more showers during winter. It's also for the purpose of warming up. But yeah, we have to classify and disaggregate what percentage is attributed to which part. So yeah. Thank you for the question.
It's a good question. A question from AJ. In Energetic network area, we utilize 600,000 or more hot water heater systems for solar soak. One of the constraints we are faced with is that there is a limit on the number of hours hot water can be turned off, resulting in only being able to shift a majority of morning use to middle of the day. Additionally, this also limits cursed in the way. Additionally, this also limits its usage for evening peak load management. Have you done any analysis on how much minimum hours of off duration in a day is required to be able to reliably do both solar soak and evening peak management in the same day without reducing custom amenity? We would like that.
David, do you want to go first, and then I'll follow up if you wanted to. I believe that's really related to your hot water shortage risk and different timers. That could be informative, or if you want anything else to say as well. Mm-hmm.
Yeah, so that is one of the challenges. We want to shift energy to the night, but we also we have shown in this hot water shortage analysis that there are critical points that we need a top-up charging. So the problem with that is if that top-up window, let's say, for example, to avoid hot water shortage risk during night, that top-up window cannot be too long, because otherwise we will be hitting the water mostly during night. So we didn't get to the point to add an additional window in this analysis, but it's definitely something we can look at.
It could be interesting adding that, David.
I have another comment, Scott. Sorry.
Yes,
so this is a very interesting and important question. And when you are controlling this amount of large water heating systems, and also wanting to make sure that you minimize the hot water running out of hot water risk, it's tricky. Now, what I can tell you, Jay, is what I've seen from different trials across Australia. This new control loads with this solar soil component, different aggregators seem to work with 7 to 8 hours of on periods per day. So 7 to 8 hours where the circuits are energized, and they allocate 2 to 3 hours of this 7-8 hours to the early morning period, say 4 to 6 or 5 to 7. And with these statistics, there seems to be very low number of complaints. Now there will be customers who'll have a lot of like some of them have poor insulation, higher thermal losses, maybe undersized tanks, some other issues that may run to this problem. But to answer your question, in these 7-8 hours of control, the majority, maybe some part can be in the off-peak periods, a couple of hours. Some part could be on the early morning, and then the remainder during the solar soak. So that way, I don't think you have any issues with the peak demand management, because during that time it will be off, and you also have at least 50% of hot water shifting happening during the solar hours. Not sure if that was helpful, but happy to follow up on that as well.
Thanks, Brian. I was going to only comment there also your message around the thermal storage efficiency of tanks and the potential to improve that would obviously play into reducing the hot water shortage risk.
Absolutely, Scott, and that's something that I would really like to follow up with industry and really get to the bottom of it. Yeah, what are the opportunities there?
So given that we don't have any further questions there, and we have 5 minutes remaining, maybe we can wind it up. Thank everybody who is still online for attending, and encourage you to come to the RACE website, and you will be able to get the full report in 3 or 4 weeks' time when we finalize that, Baron. And certainly interested, as Baran has mentioned, that if you have other areas of research that he didn't cover in the list of desires at the end of the presentation, please share those with us that we can consider those. Likewise, if you're interested in working with the team and with RACE, with funding support from RACE and the research partners, then we can potentially make this happen if you would like to get in touch. Any final comments from you, Baran?
No, thank you everyone for attending, and thank you for all the questions. We look forward to staying in touch and hearing back from you if you have any further questions.
Thank you, everybody.